So this is our last but not least time. I would like to introduce Jussi and Zoran with their presentation, Breaking Free of a Single Data Center. So I am curious, how many data centers will be then when single is not enough? Good. Stage is yours.
Let's see.
More is always better.
Yes, absolutely, yes. All right, hey, good afternoon, everyone. Thanks for sticking out here this long to join us. Today we're going to talk about a bit on the kind of architectural patterns, how you can stop thinking about clusters and as being placed in single data centers, and really embrace geographically distributed AI platforms. And of course, every tool that we're going to be mentioning, everything is of course open source, so no vendor lock-ins there. So I'm Jussi. I'm working at Mirantis as senior principal engineer, whatever that means. I've been working in the community or within kind of the community for past 10 or so years already. So I guess you could call me also hard-headed because I'm still here doing Kubernetes and other cloud native stuff.
Yeah, my name is Sören. I'm working at Lockside AI, and my origin story in the cloud native field started out with OpenStack, and then some time I switched over to containers, and nowadays I'm building infrastructure for geo-distributed AI training.
All right. Quite often when we think about platforms and especially kind of AI platforms, we think about things as really being single data center. Everything is more or less homogeneous in a way. You have same operational model for everything and so on. The reality is unfortunately quite different. One of the main drivers for that is the scarcity of GPU resources. I guess you've all seen it. Even the major cloud providers actually run out of capacity every now and then. Or at least for us who are not in the billions of dollars of revenue, we are probably the least favorable for them to actually get our hands on those resources. Or if you're lucky enough and you actually have some resources available on your own on-premise environments, those might be scattered around different data centers, edge locations, research labs, and so on. To make things even worse, you probably will run into different generations of hardware, different vendors, of course, different VRAM sizes, different driver versions, and everything. Now, we all know that here in Europe, we're kind of driving towards being sovereign, right? Which is a super good thing. But it doesn't, unfortunately, help things, because when you develop your applications, you increasingly get requirements to place different kinds of workloads in certain environments or geographical locations. So it really drives the landscape of the infrastructure to be super fragmented. So
My bad. Sorry.
So why is this a Kubernetes problem? Well, why do we want to have Kubernetes in the picture in the first place? Well, we're at KCD event, so we all love Kubernetes so much that we want to put it anywhere and everywhere, right? More seriously, I think we as an ecosystem are kind of standardizing on top of Kubernetes. So I think it's more or less nowadays like every single week there's some new AI related tool popping up that builds on top of Kubernetes and the patterns of Kubernetes, being declarative and everything. But since the fragmentation, now the workloads are actually spanning between geographical locations, spanning clusters, sites, regions. So you really have to stop kind of thinking about single cluster as your target for the workloads. It also means that you have to start thinking of managing multiple clusters. You probably are already, but increasingly the number of clusters is growing. So your multi-cluster orchestration really becomes your foundation of running AI wherever you can get your hands on GPUs. Whether you can actually order them and maybe get them like 6 months later if you're lucky, or if you can find them from your cloud provider or data center provider.
All right, yeah. So for us, this whole setup of these fragmented resources that are located across different research clusters, on-premise environment and edge environments, basically became very concrete through our collaboration with SPRIN-D, which is the German federal agency for breakthrough innovation. Basically, they are partly inspired by the US ARPA model, and they run challenge-style innovation programs for topics in which they see the potential for disruptive progress. And one of those programs is this composite learning challenge that we are a part of. And composite learning, in case you haven't heard about it yet, which I also hadn't before we started this project, is basically about combining distributed, decentralized, and federated learning mechanisms. So basically, SPRIN-D here is looking to train for approaches to train AI models across heterogeneous and distributed systems, without assuming one centralized data center where all the compute and data is co-located. So they are exactly targeting such an infrastructure that Jussi was talking about in the beginning. So when we started with this project, we wanted to approach this challenge from a systems and infrastructure perspective, because this is not only a machine learning problem, but also about how to make these fragmented GPU resources operationally usable. So this is why we started this project. And basically our goal here is to build an open and Kubernetes native operation and model, or platform if you want to call it like that, for geo-distributed AI training. And once we framed it this way, the platform requirements became quite clear to us. For instance, this platform has to be provider agnostic, since we cannot assume that all GPU capacity comes from one cloud, one provider, or one data center. Also, we need to support heterogeneous hardware, since such a GPU fleet is typically also not a uniform set of identical machines, right? So therefore, we have to deal with different CPU architectures, GPU architectures, as well as vendors and types, and their respective software stacks. For instance, CUDA for NVIDIA or ROCm for AMD. So therefore, this hardware diversity must become a managed platform concern, not a manual per site work. And finally, in this process, we decided early on that we wanted this platform to be Kubernetes native, because we want to build up on these Kubernetes APIs and use and build upon the cloud native ecosystem that is already out there, instead of reinventing the wheel and building our own separate infrastructure control plane here. So after we have thought about these requirements, right, we started out and looked around to find out what is already out there and what Kubernetes native building blocks we could maybe build upon. And that is how we found this Cosmos open source ecosystem that Jussi is going to talk a little bit about now.
Yep. So how do we get from this fragmentation to really get like a unified platform that we can actually treat as a single platform? If we think about the foundational level, kind of the sort of the infrastructure level of things, each of the environments have different operational constraints. In one data center, you might have some operating system images available, some other site cloud provider has some others available, or at least different versions. And it basically means that every single environment you deploy to, it is actually different. How much different, that's a different discussion, of course. So for the foundational level, we want to have Kubernetes as boring as possible. That's where the k0's CNCF sandbox project kind of comes in. It provides us, well, the Kubernetes, of course, but it's really built as a kind of a minimal possible Kubernetes package in a way. So k0 distills the whole of Kubernetes into one single binary file, which has virtually zero dependencies. Everything is actually statically compiled, so I can drop the exact same binary on Ubuntu, Red Hat, Alpine Linux, whatever. It just works. Going kind of one ladder up, we need to start thinking about clusters, and as in many clusters. So to be able to cover this kind of archipelago of different sites and cloud providers, you will end up having multiple, and I mean really many clusters to manage. So we all know that cluster lifecycle management can be a bit slow and hard and daunting, especially from the control plane nodes point of view. I guess we've all been able to break down etcd. I've done it many times. Just last week, I found another way to break it down. So the second kind of piece of puzzle is a project called Cosmotron, which is kind of like a sub-project of k0s in a way. It really builds on top of Cluster API. What that actually means for us is that our clusters now become custom resources. So essentially, you can actually define the cluster configuration, the infrastructure configuration, everything as a set of custom resources. The super nice thing about that is that everything is now declarative, which means that you can start to do GitOps patterns for clusters. And also, we get standardized lifecycle model and operational model for every single cluster that we have. Now that we have capacity available for us through multiple clusters, our kind of GPUs and compute resource in general, it's still kind of siloed because it's dependent on a cluster in your typical model, which means that scheduling things, for example, is actually bound to a cluster. Kubernetes scheduler understands only about single cluster, of course. The third piece of puzzle is open source project called Cordant, where we build on top of Cluster API and Cosmotron and others, where we really enable fleet level operation. What I mean by that is that you can actually start to schedule and deploy your applications across fleet of clusters. You can say that I want to deploy my fancy AI workload to every single cluster that has GPU resources or matches this label or whatever patterns you want to do. So we can actually start to treat the whole capacity and GPUs more like a shared pool of resources. I mean, of course, kind of almost physically thinking, GPU is bound to a cluster. But now we can actually access that at the fleet level. And more importantly, we get a homogeneous model how we operate our every single cluster and basically our whole fleet of clusters. And of course, observability is the same and everything.
All right, so now that we heard a little bit about those components, let's see how we use them to build up a platform or build upon them for a platform for geo-distributed training. And let's connect those back to the initial requirements. Just to recall really quickly, platform had to be provider agnostic, support heterogeneous hardware, and be Kubernetes native. So to comply with the provider agnostic part, we built up on Cosmotron, which allows us to run both the control planes in a single management cluster. So basically, we can spin up a single management cluster, deploy Cordant on there, and then use Cluster API from there to onboard GPU nodes or attach remote worker nodes, so to say, from anywhere. So they do not have to be located in the same data center anymore. In addition, it allows us to separate the control plane traffic from the data plane traffic, which is quite essential for AI training later on. To support heterogeneous hardware, we're using k0s because, as Jussi said, it's a lightweight Kubernetes runtime which basically runs anywhere. Therefore, it also works great on heterogeneous hardware. And finally, we're using Cordant, which allows us to orchestrate this whole life cycle declaratively. Basically, Cordant has this concept of cluster templates, which are essentially blueprints for cluster API clusters that we can use to provide a blueprint for our ML engineers to deploy their own clusters and run their own workload on there with service templates that are used to deploy, for instance, the GPU stack, the GPU drivers, as well as the workload itself. So these components therefore allow for a workflow that goes from creating a hosted control plane in a management cluster over to onboarding GPU workers and deploying the platform services as well as the platform itself declaratively using templates. And since those are basically templates, right, or CRDs, we can put them in Git repositories and use GitHub's workflows to organize all of that, review it, and make it auditable. So basically, this is the foundation on which we build up this platform. And after we done the work and figured it out, we switched gears a little bit and moved over to a validation phase, in which we run different field studies to validate if it's possible to use such a platform to run geo-distributed AI training. Once, for instance, across heterogeneous hardware. And in another field study, we started a more dynamic approach where we used excess energy to train LLM models. So here you can basically see the setup that we created for our first field study, which was about the geo-distributed training on heterogeneous hardware. And let's address the elephant in the room first. Distributed training typically assumes that GPUs are co-located in a node or at least in the same data center and connected via fast interconnects such as NVLink or InfiniBand. This is obviously not the world we are targeting here, and therefore we intentionally violated that assumption for this field study and created a setup where we started out with a management cluster that is located in Germany, where the whole Cordant and cluster API stack runs. And from there on, we attached GPU worker nodes from 2 different data centers. For instance, we used NVIDIA nodes that were located in Canada, and also AMD GPUs that were located in the US. So here, this whole field study was designed to validate whether we can make this cross-border and cross-vendor GPU resources work together as one operational training environment. And for such an environment, one of the most important things from a platform perspective, except obviously having the money to pay for those GPUs and then being able to find a GPU provider, which still has those GPUs available, is the cross-site worker connectivity. And for that reason, we basically created a Cordant cluster template in which we integrated the CNCF project Cilium as a Kubernetes CNI. And there we also configured Cilium to build up secure peer-to-peer WireGuard tunnels between the participating workers of the clusters. This, on the one hand, is great because it avoids a central VPN gateway through which all traffic would flow. And also, Cilium allows us to build up on their service mesh implementation to even connect clusters between each other. We also tested other overlay networks, but here for this case, we decided to use the Cilium and WireGuard approach since it keeps the networking closer to the actual Kubernetes data plane. And if you look one layer up, you can see some of the services that we installed on those clusters. And basically, since we want to run AI training, we need to get the GPUs to work, right? And in order to get them to work, we need to install drivers. And for that reason, we employed the NVIDIA GPU operator to install the CUDA runtime on the actual nodes that had NVIDIA GPUs, as well as the AMD ROCm GPU operator that does the same for AMD GPUs. And then we also deployed Volcano. Volcano is another sandbox CNCF framework, which enables gang scheduling, which is quite important for AI workload. Yeah, and then we started implementing the actual training, which was done by our engineers with PyTorch Elastic and then run as a Volcano bash job. And don't worry, this is not going to turn into a hardcore ML talk right now, but you can't really use normal distributed data parallel training in such a scenario because the latencies are way too high. And therefore, we built up our training method on an approach that is called DLOCO. It stands for Distributed Low Communication Training, and was published by Google, and we extended it a little bit and deployed or basically implemented our training algorithms on there. As I said, I'm not going to go into much detail here, but you can approach me after the talk if you're more interested in that part. So basically, we had our platform ready, and we also validated it by implementing different workloads. So basically, we trained different models from different workload classes in this platform, or on this platform, better said. For instance, LLMs, computer vision, graph learning, reinforcement learning, and audio. And that worked out actually quite good. We were able to achieve a comparable performance when it comes to the actual accuracy of the models later on, with some caveats that I'm not going to go into detail right now due to timing issues. But yeah, in general, this low communication training reduced the WAN pressure, the pressure on the internet level. If you're interested in the actual methodology about it, we published 2 papers about it and also open source the whole training implementation, or you can approach me if you want after the talk. Okay, so this was the first field study in which we basically assumed a rather static pool or environment of GPU resources, right? For the next study, we wanted to relax that assumption and target a more dynamic approach in which GPU resources can come and go over time. And the motivation for that actually stems from the sustainable computing domain. Because here, the point is that the renewable energy is often not always produced where and when it is needed. For instance, wind and solar power might be available in one region, like here on the slide in northern Germany, whereas the main consumers are somewhere else, for instance, in the south of Germany. And if the local demand is then too low, the grid is congested, or there's not enough storage available, this excess energy would go to waste. And this is something that is called a curtailment window. So basically, you have a curtailment window when there is potentially useful energy, renewable energy available that cannot be consumed, moved, or stored economically. And so basically here we asked ourselves, what if we could create some kind of elastic AI workload that could move towards these temporary windows of excess energy and use them to, for instance, train an LLM model. So that is what we tried out here in this field study. But this is not, again, not only a machine learning problem, but also obviously an infrastructure problem. Therefore, we require an elastic infrastructure orchestration layer. To walk you through our approach real quick, we basically assume that we have multiple geographically distributed sites available. Here, in this case, the site A currently has excess energy, so it is active and also training locally. Site B instead does currently not have a curtailment window, so it is not provisioned, the nodes are not running, it's not using any energy, and it's also not training. But when site C enters the curtailment window, and at that point in time, this site is provisioned, the nodes are prepared and attached to the training environment and can also start training locally. And as soon as we have multiple sites active, this purely local execution is switched to a federated mode, basically following the federated learning paradigm, where the model state is periodically synchronized between the participating sites and then averaged by, for instance, a federated averaging algorithm. And from a machine learning perspective, we implemented that using the Flower AI framework. This is like one of the biggest open source frameworks for federated learning right now. So all of that was mainly about the AI side, ML side, right? What did we have to change in the underlying platform to enable this training? And the answer is actually not much. It's exactly the same platform. We just integrated or added 2 further components. On the one hand, a curtailment signals API, which provides us those energy availabilities or curtailment window signals, if you want so. And a scheduling API, which receives those curtailment signals and then decides based on those data what site should be activated and what other site should be turned down. So basically it converts these energy signals into resource lifecycle decisions by, again, talking to Cordant, which then uses cluster API to spin up a site, spin up a cluster, attach it to the training environment by installing the GPU operators again, starting the actual training workload, and so on. And here we even extended, or here we had to extend it by implementing a custom Kubernetes operator for this Flower framework. But this is still, again, cloud native stuff, right? We all have probably written an operator at some point in time. And yeah, so this also worked out quite well, actually. And we were able to train a 500 million parameter transformer model on this infrastructure. And during the training, we switched between local and federated execution while preserving the training quality. And at the same time, we could reduce the operational carbon emissions by more than 90% in times compared to a baseline execution where only one of those sites would train the model. Again, we wrote a technical report about it. We also open sourced the code for that, which you can find here on the slide.
I wanted to point out that although this is about, or this field study was about these containment windows and model training, the exact same pattern can be used for any signal that you want to do. Whether it's when your application users wake up and start to use your application like time-based things, or it doesn't matter what the signal is. You can use the exact same pattern, just match to the signal that matters for you and your applications and environments.
Exactly, yeah. All right, so what did we learn during these field studies? First of all, we learned that it is possible to run geo-distributed and heterogeneous AI workloads. So they are viable today, and building on top of this Cosmos ecosystem and cluster API and the whole cloud native ecosystem, we had a stable foundation where we could even go from a rather static training to a more dynamic approach without changing the actual underlying platform at all, which is great in my opinion. Another thing that we learned is that GPU lifecycle management can still be hard, especially for heterogeneous environment. I mean, it's not as bad anymore as the meme here on the slide may make you think, because we have these operators for NVIDIA and for AMD, but we still ran into problem when we, for instance, used an instance which already had drivers installed, because then the actual NVIDIA operator in that case runs into problems, since there's already a driver installed, maybe in the wrong version, and then it fails, and then we couldn't run the AI training anymore. In addition to that, we had similar problems sometimes with the AMD operator, because there, when you want to automate the actual install form or the actual deployment of those drivers, you need to prepare images for each Linux kernel version the driver should be installed on. This is not a problem. We did that for like the last 10 versions of the Linux kernel. But then we tried to run, for instance, on cloud providers which have their own kernels, and then it didn't work out again. So it can still be a hassle. It's not as bad as it was, but yeah.
It's still not great.
It's still not great, so to say. Great,
Yep.
yeah. Finally, secure peer-to-peer networking works, but the latency-sensitive training still needs care. And this also brings me to the last point I want to make here, is that the platform and workload must be co-designed. You can create a platform like that. You can connect it. It can look like an operational platform, even though these remote workers are globally distributed. But as long as the training does not take the latency, for instance, into account, it's not going to work out. So you have to work on in both direction and combine the work there.
Absolutely. And one thing I'd want to point out also is that the one of the kind of enabling concepts was the whole fact that through cluster API and all the other tooling that we introduced, everything is now declarative, which is actually the enabler to build all this scalability and implementing the containment windows and deploying clusters like very, very dynamically.
Yeah.
So that's definitely a direction to look into in your use cases too.
All right. With that, thank you very much for your attention, and we can open the Q&A session. Yeah, the first question I actually anticipated, because I also watched this talk yesterday, and yeah, this is actually something we're currently looking into. We started out with the training side of things, but inference is definitely a case which would also work. And I think Mohammed yesterday even described a scenario or an architecture which is quite similar, right?
Yes.
It would work for that.
It absolutely will work for that. Of course, it depends on your application, whether your application stack allows you to, or the nature of your application allows you to do this. But from the like Hami, Kaito, Cluster API point of view, it'll work exactly the same. Because in the end, those are things that you deploy as pods in your cluster, so it doesn't really change the equation that much.
For the second question, which is about the networking side of things, we are basically using Cilium here, right? And for the actual AI training, we don't really need ingress because the AI training is deployed via GitOps. Our developers could just hit an API and then basically deploy the actual training. So there we don't really need ingress, right?
Yep.
It is more important for inference scenarios, actually.
Absolutely, yes.
Yeah.
And for those use cases, I don't know if Yuri is still around, but there are very nice tools in the CNCF ecosystem. For example, this KGB, the global load balancer thingy. I don't really know much about that, but I know that it exists, and so you can absolutely make it work for inferencing and basically any other types of workloads too. How does the DNS side works? Well, when does DNS actually work? Well, that's kind of outside of the platform per se, but I bet you can do like geo-distributed routing through DNS too if you really are up to that. Kera for scaling with the cluster API. To be honest, I haven't tried and looked into that much into Kera for cluster API. I do know that you can actually integrate the so-called standard Kubernetes cluster autoscaler with cluster API, so that the autoscaler would actually scale up the machine deployment in cluster API. With that pattern, which I really, really like, because in that case, you don't actually have to configure the autoscaler to talk to Amazon or Google or whatever at all. Autoscaler only talks to cluster API, which is kind of the abstraction in between. So it makes the configuration and setup very, very simple.
Yeah, if I may answer that one. We actually validated, or we conducted this feed studies in order to validate how stable it really is. And I would say from a platform perspective, it's quite stable actually. All those cluster API things and the magic behind it works quite well. What sometimes makes issues or has issues here is the actual ML side, the workload side, which also refers back to the last point I made in the lessons learned. Both of them have to be co-designed and co-developed. And this is actually an ongoing process. Google just released a new paper where they extended the local approach, for instance. And then we have all those different federated learning approaches, which also work for that reason and make it hopefully more stable. Yeah.
Yep. All right. Thank you.
Thank you.